Next, we're going to talk about expectations and variances. And my goal for this video is that I'm going to simulate dice rolling with different probability distributions. And then I want to verify that when we are doing all those theoretical calculations with expectations and variances, they may be empirically verified or numerically verified by simulating those dice rolling. Okay, let's see how to do this. So first, let's assume I have a dice. The values are 1 to 6, and I have their probabilities. I want to start from a reasonable or typical dice. So all the probabilities are 0.167, okay, 1 over 6. So in that case, I'm going to focus on some theoretical calculations first. So first, I want to get the expected value or expectation. So I hope you still remember how to do that. Basically, it's just a sum product because expectation is just a weighted average. We do a weighted average of our values, possible outcomes, according to their probabilities. Okay? When you roll a dice, your expectation or your mean, let me do it expectation, is just 3.5. Okay, very typical, 3.5. And then I want to calculate the variance. So for the variance, what I should do is that for each possible value here, I want to find its deviation from the mean. And then I want to square it. Okay, so I get all of this. And then I do another sum product. Those square deviations weighted average according to their values. Okay, so here I don't need to fix it according to their probabilities. Okay, 3.91. These are their its variance. Or if we are talking about standard deviation, it's the square root of that. So that's nothing special, just theoretical calculations, theoretical derivations, plugging numbers into those formulas. That's it. Okay, so that's fine. But what I want to do now is that I want to do some dice rolling and then see that these theoretical values are indeed making a lot of sense. So let me see how I may do this. What I'm going to do is that I'm going to roll dice, right? So I'm going to use rand here. So that means I roll a dice once and get 0.333. How should I know which dice value that corresponds to? I can do the thing that I just did when we are simulating discrete random outcomes. So I'm going to get the lower bound here. I understand that it's from 0, and I also understand that it is something that corresponds to this value. But of course, because later I need to do some kind of cumulative distributions, so I'm going to do this. I'm going to do sum from this one to itself. If you feel somewhat weird like why I'm doing that, when I scroll everything down, you will see it. Okay, this value is the sum of those two. This value is the sum of those three, and so on, and so on, and so on. So these are the lower bound of each intervals here, and that is how I may do the lookup thing. So my lookup value is here, my lookup vector is here, and my lookup result is here. Okay, when my dice rolling is 0.23, I get 2. When my dice rolling is 0.44, I get 3. So let's say I roll the dice. Let's do it 100 times. Okay, so I roll the dice 100 times. Then column B precisely records the outcome of roll the dice 100 times. Now what I want to do is that beside these theoretical values, I want to do an empirical values. So how do I get the empirical values from dice rolling? If I want to calculate the expectation in this case, then it's nothing but the average of all these 100 dice rolling, right? That's 3.56. We know that it's not going to be exactly 3.5, but no matter how you change your dice rolling outcome, your result will be roughly 3.5, close to 3.5. It's quite impossible for you to see a value that is lower than 3 or above 4. You may try it by yourself. If you don't roll the dice for 100 times, if you do it for 500 times, 1000 times, then your empirical value will be very close to 3.5. How about variance? Okay, we're going to do variance, and here is variance for sample or population. Well, in this case, it's for population, because when we are doing all the calculations here, the theoretical function, the theoretical formula we use is for population. So we can select all the values here, and then we can see, okay, it's 3.1, somewhat close to 2.9. And then you roll the dice many times, 2.92, 2.73, 3.1, 2.9, 2.8, 3.2, 3.0. Again, the variance is close to the theoretical variance. Sometimes you are lucky, sometimes you are not, but it's not going to deviate too much. And finally, of course, for standard deviation, I don't want to try it anymore, because if the variance is close, then the standard deviation, of course, will also be close. Okay? So let me try to do this. I'm going to extend these values from 100 to somewhere else. Okay, how about this? I'm going to try 500 or more. And now, for each value here, I want to select all the values in column B. Okay, quite close to 3.5, right? And here, I also want to change it to all the values in column B. Okay, also quite close to 2.9, right? And then now, if I keep do the dice rolling thing, we can see the deviation somewhat is smaller than when I was just using 100 values. And that makes sense, right? If I keep do the dice rolling thing and I do 1 million times, 1 billion times, it will be just so close to 3.5 and 2.91, of course. So that's how we somewhat verify that when we do the theoretical calculations, we do it from the theory parts. But we don't need to do that in some sense, because as long as we are able to use computer to simulate a lot of random outcomes, then their average gets the theoretical expectation. Their variance gets the theoretical variance.